All right, so this is the last section in chapter 7 on exponential and log models. So this is learning target 24. We're looking at modeling exponential growth, decay, and a few other types of exponential models. So this is logistic growth, Gaussian growth, and logarithmic curves. And so let's start off with exponential growth and decay. These are the things you're familiar with, probably, thinking about exponential functions, where you have a growth model and you have a decay model, where the values are increasing by a constant multiple rather than a constant difference. So in this case, if it's growth, the model we have is a times e to the bx. So we're using e as a standardized base for our functions, and we're manipulating the factor of multiplication with this b value up there. The a value tells you what you start off with. That's the initial value you have. And so if it's growth, you get a times e to the bx, where a is bigger than 0, b is bigger than 0. I have a typo here for the second one. For decay, this should be y equals a times e to the negative bx. B is still positive, but you make it negative by adding that negative sign in front. And that way you get decay. So we have this model given to us. P equals 800 times e to the 0.05 t. So initially, what is the size? Well, we know that the initial value is that a value in front. So the initial size is 800. But we can check that by putting in 0 for t. Right, so if I substitute 0 in for t, that's going to make this e expression, the exponent, raised to 0. Well, anything raised to the 0 is just 1, so you get 800 times 1, and that gives us 800. So that's why that first number is always the initial value, because when you plug in 0 into the equation, the exponential value is going to go to 1. Now we want to know how long it will take for the population to double. Again, there are two different ways you can do this. So one way is we know the initial is 800, so to double it needs to become 1600. So we can check when 1600 equals 800 e to the 0.05 t. And then we divide both sides by 800 and take a natural log on both sides. And divide by 0.05. And that gives us natural log of 2 divided by 0.05 is about 13.863 years. So that's one way to do it. Another way to think about this is because exponential growth with the e value, it's really all about ratios. Exponential graphs look the same everywhere if you zoom out or zoom in at the correct amount, which means it doesn't matter where your initial value is. What matters is that b value. And so whether the initial size was 400 and I wanted to see how much it will double, like if I started off with 400 people and I wanted to know how long it will take for the 400 to double, or if I started with 2 people and I wanted to know how long it will take for 2 to double, with that b value, the doubling time is going to be the same regardless of what the initial value was. You can see that because once I started solving this, I plugged in 1600 equals 800 here, but immediately when I divide, I just get 2. That's the doubling. And then there's no initial value here anymore, which means if I say I had initial value was 500 and I wanted, so my population would be 500 e to the 0.05 t. Well, then to double it, I'll need 1000 equals 500 e to the 0.05 t. Divide both sides by 500, and I get the same equation again. And so when I solve it, I'll still get 13.863 years. So when you get these rate of increase, like doubling, tripling, quadrupling, 5 times, 6 times, stuff like that, it doesn't matter what the initial value is, because the time it takes to double or triple is going to be the same regardless of what you had to start off with, because that is controlled by the b value, the growth rate value, not by the initial value at all. So you could just skip that initial line. You know it's doubling, so you know it's just going to be 2 equals e to the 0.05 t. you want to be careful with that though, is when you do it like this, there shouldn't be an initial value here anymore. The initial value should be 1 in that case. The next thing you have is a carbon dating model. So that also works with the exponential growth and decay. In this case, it's decay we're looking at. So this is the ratio of carbon 14 to carbon 12. Present tells you how long it takes, how old a fossil is. So in this case, we have the ratio is 10 to the negative 16. We want to know what the age of the fossil is. So we know this model is given to us. And we know that r is 10 to the negative 16. So again, in this case, we're just solving this equation for t, which means we can multiply 10 to the 12th on both sides. So this is going to be negative 4. E to the negative t, 8223. We take the natural log on both sides. Hopefully this stuff is stuff you remember from the previous section to solve equations. It's really not much new in that case. When we take the natural log, the e goes away. And so then to solve for t, it's going to be negative 8,223 times the natural log of 10 to the negative 4. So natural log of 10 to the negative 4 times 8223. My calculator is taking some time to figure that out. Got 75,736.629. Not sure I trust my calculator because it was being kind of weird. But this is the expression you would type in. And then I think that's the number you should get for that. But I'm not exactly sure based on my calculator right now. So those are your growth and decay models. Excuse me. The next model you have is the Gaussian model. So this is a model that's used in probability and statistics a lot. And the Gaussian model represents populations that are normally distributed. So if you think back to learning stats last year, you probably talked about normal distribution a little bit, and you might have talked about z-scores a little bit. Normally distributed populations are things that kind of fit this bell curve model of data distribution, which means that the mean of your data, the thing that's like the standard average of it, is right in the center of your data. That's where 50% of your data is above it, 50% of your data is below it. So basically it's saying the mean and the median of your data is the same. Then you can go with standard deviations out and you can calculate the percentage of how much data is on either side. So you get this bell curve. Right in the center, that would be your mean. And if it's perfectly normally distributed, the mean is also the median. That's not always true. And the way this is constructed is using the mean. And then we calculate the standard deviation. And we can go like -1 standard deviation on the left, +1 standard deviation on the right, then +2 standard deviations, -2 standard deviations, and so on. And then the area under this curve tells us what the probability is that a randomly selected data point is in that range of data that we have. So everything here is 50%, everything here is 50%. This is like 34%. There was the empirical rule. You probably did that. You don't need to know that for this class. But you should understand the model is an exponential equation. So if you go on to, in calculus, you'll see how to actually calculate the area under this curve. And if you ever do a stats with calculus class, then you'd actually use integrals to calculate these probabilities. If you're taking a stats class without the calculus, such as AP Stats or a lot of introductory stats classes in college, you'll get tables that do all those calculations for you, so you don't actually have to do the calculus for it. But you should know now that you know calculus, you understand some of it, you can see how those values were calculated is using some calculus to figure out areas under these curves. The general equation looks like this. It's a pretty complicated looking equation. And the a value, basically, that's where you put in your mean and your standard deviation, and that's what calculates the curve for you. And you don't need to know how to come up with the equation, but you should know how to recognize the equation. So if you see an equation like this, you should know that's a Gaussian model. All we want to do here is it's a sketch to graph the function, but it's always sketched for you. And we want to estimate the average math score. But if you look at this, we try to estimate the average score. Well, that's the 515. Right, so basically on the Gaussian model, we want you to understand the graph of it and recognize the equation, but you don't need to do much more than that. We're never going to ask you to write the Gaussian model for something, but you should understand what the Gaussian model is and recognize it when you see it. I'm not going to spend too much time on that. The next one is logistic growth. Logistic growth is something we see a lot of nowadays, because logistic growth models is how viruses spread. It's how population grows. It's how a lot of exponential growth actually happens in the real world. So exponential growth grows indefinitely, infinitely. But that's not what actually happens in the real world, because in the real world, we have logistical constraints on things. We have amount of money, amount of resources, amount of food, amount of space that limits how much we can grow. So we can grow exponentially, but at some point it's going to cut off. And so you get this flattening out at the top, right? So like now in the news, we talk about flattening the curve a lot. What does that mean? We're flattening this curve so it doesn't go exponential, right? If we didn't flatten it, it would continue exponentially. Instead, if we start flattening it, it goes this way. We're changing the concavity on the curve, right? If it's exponential, it's going to always be concave up. What we want to do is find an inflection point that's going to make it concave down. And that means the rate of growth is decreasing. So it's still growing, right? This function is still increasing, but the rate is decreasing. It's not growing as fast anymore. So that's what we're trying to do with all of the coronavirus stuff. So usually this is used to model populations with some sort of constraints, right? Usually it's called a carrying capacity in biology. It's also called a sigmoidal curve, apparently. I've only found that out from your textbook. I've never called this a sigmoidal curve in my life. Sometimes you'll see it called an S-curve as well, because it kind of looks like an S. And the main things to realize is on this bottom half, that's concave up, which means dy dx is getting bigger, right? It's increasing. And then on this top half, it's concave down, and so dy dx is getting smaller, which means the rate of increase is decreasing. Right? So if you think about it in terms of like the coronavirus cases, if we had like 100 new cases added in one day, but then the second day it's 150 new cases, we have more cases because now we have 250 total cases, and the rate of growth of those cases increased. It was only 100 the first day, but then 150 the next day. But then if we go from 150 and then the next day we only have 90, now it's gone down. We still have more cases overall. Now we have from 250, it's 340 cases, but we didn't increase by more than 150 cases. We only increased by 90 cases. So the rate of growth is decreasing, even though the actual value is still increasing. That's what a logistic growth model does. The equations for this look like this equation. You have the capacity, the top bit that's going to limit growth is on the top of your fraction. And then on the denominator of the fraction is where that exponential function happens. So this is really a rational function with an exponential function in it. Usually a carrying capacity is the population, right? So that's the limit. You could get everyone infected by something or a maximum amount of growth that your environment can support. You can get up to that point, And then the exponential function on the bottom is going to make that exponential growth happen. But the rational function part of it is going to kind of like asymptote it in a way that flattens that top part. It's not an asymptote as such, but it's kind of like that. So let's look at this example. We have a college campus of 5,000 students. One student comes back from vacation with a contagious flu. These examples were written generally, right? But it seems very applicable right now. So that's kind of where this is coming from. So we have the spread of the virus is modeled by this equation. And we're looking at how many students are infected after a certain number of days. If more than 40% of students are infected, that's when the college is going to call it to cancel classes. So we want to know how many students are infected in 5 days. Well, for 5 days, that would be t equals 5. And so we can just use this model. For the logistic growth model, we want you to be able to recognize it and be able to write these equations to a certain extent. Writing as in you should know where the top number goes. You should be able to like substitute values, and you're not coming up with the total equation yourself. In this case, you just type that in your calculator. Be careful when you're typing it in because there's a lot of different moving parts in this. But type that in, see what it equals. The next thing is how long will it take before classes are canceled? Well, here we know 40% of students need to be infected, which means we need to get to 2,000 students. And so then you do 2,000 equals this. And this is something where you'd use a graphing calculator to solve the equation. So this is another place where you should learn how you use your graphing calculator for it. You can either go on Desmos to try it out, but also try it on your actual calculator if you have one at home, because that can give you practice with using a graphing calculator and helping you out for in the future taking an SAT 2 or an AP test where you have to use a graphic calculator and you don't have access to Desmos. So that's a logistic growth model. It's probably the most applicable real-world model that you're looking at. That's used a lot and very frequently. And you should know how to, again, use a calculator to solve things like that. You have an example of this whole problem worked out in your textbook as well, so you can look in your textbook to check your work on it as you work through it to see if you're getting the same answer. The last one is logarithmic growth models. So this is again using that log scale to solve things, except here we're not making both x and y a log scale value. We're only making x in a log scale, and then the y is still the actual value. So this is how we calculate things like pH, and we calculate POH, and we calculate magnitude of earthquakes. So these are things where the values vary a lot between each other, so it's not really practical to count them, for example, from 10 to 100 to 1,000 to 10,000. Instead, we just count it in powers of 10. So we count 1, 2, 3, 4, rather than 10, 100,000, 10,000, because the space in between those are so huge, your graph would have to be huge, or you'd have to shrink that graph down so much that it's really impractical to look at it anymore. So these models look like kind of like a line graph where you have a log on the x value. Very popular example of this is the Richter scale, which is used to measure the intensity of earthquakes. And so this equation is really just a scaling of using log base 10, where you have a minimum intensity of an earthquake, which is standardized as 1, and then you have the intensity that they rate it, which is like the wave energy measurement of the earthquake, and then they give it a ratio based on that. So for example, if we had an earthquake in Nevada in 2008 where R was 6, the Richter scale value of that earthquake was 6, then we can calculate the intensity of it, the wave energy, by using this equation. We know R is 6, and it's log of I divided by 1, the I0. And so if I raise both sides by 10, we get 10 log I, which is 10 to the 6 equals I. And so that's how this Richter scale works. It's really just powers of 10 as magnitudes, because 10 to the 0 would be where that 1 is, and then you're comparing magnitudes of 10 after that. So the next one is an earthquake in China where the Richter scale value is 7.9. So again, we can do something similar, right? And so now we do 10 to the 7.9 equals I. And so now we want to know, what is the increase in the intensity? Well, what we want to make sure is that the Richter scale value went up by 1.9 units. Up 1.9 units. That doesn't mean that the intensity went up 1.9. It means that the intensity increased a lot more. Right? The intensity, this is about 79,400,000. And then this is 1 million. So the actual intensity increase was quite a lot more, right? It was about 79.4 times the intensity. So even though this is a really small number, it just like went up 1.9 units, that represented a change of multiplying by 79.4, which is a huge difference, right? It's not just like plus 1.9, it's times 79.4. So this is kind of how you want to like be careful when you look at log scales, because it's deceptive in that the goal of a log scale is to make these differences smaller so you can perceive it better, but you also want to be careful when you look at those smaller differences to know that the small differences actually represent a huge difference in terms of multiplication rather than just that like small addition difference. So those are your 5 models to know. With these models, you want to be able to recognize the model. So if you look at the equation, you should know which type of graph it's going to make. So growth and decay, you should know it's a regular exponential growth or decay graph. With a Gaussian model, you should know what the equation looks like, and you should know it makes this bell curve. With a logistic growth, you should know what, again, the equation looks like this. It makes an S-curve type shape. And with a logarithmic growth model, you should understand that log scale difference. The majority of the work you'll have and the examples, problems you have are things where you have to just use a model given to you to find different things in it, or you should be able to recognize what type of model it is. You're not coming up with the models yourself for the most part, but you should be able to use these models and be able to understand the purpose of the models. So that's it for chapter 7, and then we just have one more chapter in the textbook, a few sections of that, and we'll do one supplemental thing, and that will be all your content that you need to know for this year before you move on into next year.